Okay, now you move on over to page 23. Here we are. And this is the finalization of the work energy connection. It's no different than what you already learned. Just another reminder so it's a little less awkward for you. All right, so we'll talk. I'm going to make you a separate video. It's kind of a unit review, help you think through what we've already done. So let's jump down to the middle of the page. You now have this equation. Write it down. This is from PRT6. W equals FD equals delta ET. This is a general equation, meaning they did not take the space to write this out for each specific work related to each specific force resulting in each specific energy change. They gave you the general equation. It is your job to apply it specifically. Now, there is a little bit of a tell here, meaning because they gave you the generic one and you have to apply it specifically, and this is Regents physics, they usually set up the scenarios to be pretty straightforward. You know, you're going to AP, they'll be less straightforward. But here, they're pretty straightforward. Probably the most, I guess, complex of the problem types is the ramp. The ramp, you often have an external force, a friction force, a gravity force. So you can deal with it. And also the net, you know, they'll tell you whether it's constant velocity. So you could potentially deal with 4 different types of forces, 4 different types of energies. So the ramp is a nice kind of combo problem where you see this in its most complex form in our class. Anyway, we've seen this before. What you need to think of is this. What type of force? Well, if it's Fg, you don't have to write this here, you just watch it. Then the work done will be Wg, and the change in energy done will be Eg or PEG. If it's Fs for force on a spring, well then the work done will be spring work. The energy change will be the PES. If it's friction, force of friction, then the work done will be WF, and the change in energy is going to be the Q, energy friction. You know, I'll put EF down here. And hopefully you're getting okay with this. Like EF, energy of friction, is just Q. And of course, finally, if it's the net force, we sometimes call that the net work or the work done to accelerate. You might more frequently see it as a work done to accelerate. And that'll be the change in the energy of speed, aka kinetic energy. Okay? So we've been doing this. We've been doing this. Here's the comments. The type of force determines the type of work. The type of work determines the change in, the gain or loss of the type of energy. The type of energy gained or lost gives you the type of behavior. So look at this. This is just saying FD, right here, equals W, right here, equals change in energy type, right here, equals behavior. And the behavior is a change in height, a compression or a stretch, a speed, heat. So this little table down here is a beautiful table. Truly, I'm very proud of this table. Anyway, the point is, when they ask you about work, we practice this a lot. Look at which work they're asking about, align it with which force goes with that, and then of course you got to line up the displacement. That's that dot product. We spent a fair time on this, so we don't need to go over that now. The new thing here is this mid part. That work leads to the change in energy. So if we turn page 24, we'll do a little bit of quick practice. We're not going to run through the numbers. You can run through the numbers. The answers are there. Let's just look at what they're asking. Here they're asking for the change in potential energy. That's a delta PEG. If it's a spring, it would be a PES. And it's lifted from 2 meters. There's a distance or a height. This is like an initial height. To 7 meters. That's a final height. At a steady speed by a force of 20 newtons. That's an F. And so in case you need it, if this thing is being lifted at a steady speed, here's the FG. Here's the F. You can call that an F external, doesn't matter. These two are going to be equal to each other. the F net over here is going to be 0. So if we're really being thorough, make yourselves a little picture, blah, blah, blah. All right, so delta PEG, there's one way, if we just look at our equation, you could write out all your givens, you should. But if you write out your equation, one thing we know about delta PEG is, of course, mg delta H. But now what you're also allowed to know is that this is going to be work, which is going to be FGD. Or, since FG and F match each other, it's going to be FD. Technically speaking, for those who care, you don't have to worry about this at this point. This would actually be negative FGD because the displacement is upward. And so it's a cosine 180. But anyway, there it is. You can do this any way you want. PE, work. You know, I could even write that in here. WG, which by the way is going to be the same as the W external in this case. I'll just call it W since we just called it F. Let's erase that little bit right there. And technically speaking, it's really the negative of the WG, but it doesn't matter. Don't worry about it. Okay, look at all these different things. The point is this. When you come to solve these problems, you could either solve them with F times D, or you could solve them with MGH. Both will get the answer. When it comes to solving for PES, you can use half kx squared, or you can use Fx, because work was Fx. When it comes to solving for KE, you could use half mb squared, or you can use F net D, because work and KE, same thing. And for the work against friction, the only equation you really had was the FFD, so the friction times the distance. And so now, this is really a nice new one over here. You've been saying it out loud, but now you actually equate them. So the first one up here was pretty simple. You didn't really need work energy to figure that one out. But this one's a cool one. Determine the elastic potential energy. I'm going to jump straight to the equation, save you a little time. You want to find PES. And normally you would just say, okay, cool, half kx squared. That's what I want. But look at your givens. You're like, whoa, whoa, whoa. X and an average force of 25. Well, that doesn't fit these. Well, that's when you're allowed to make the work energy connection. PES is also work, which is also, this is an FS, FS, X. Those of you who are trying to be a little careful about this, it's technically average FSX. And notice they put the word average in here. So if you ignored it, you get it anyway. So you can get PES with half kx squared or average F times X. Both of them do it. They gave you F and X. That's the way to do it. How about this one? How much work must be done to bring a bike traveling at 20 meters per second to rest? Well, what work is this? Well, it's not like lifting stuff, so it ain't WG. It's not a spring. Oh, you're accelerating. You're slowing down. This is an accelerating work, aka net work. And so the way you would typically answer this is you would just say F net times D. And here's the thing. They didn't give you F net and D. They gave you mass. They gave you VI. They gave you VF. You're like, huh. So I'm going to get W with M and V. Oh, yeah, you are. Because W also gives you the work to accelerate, gives you the change in KE. And in this case, change in KE, which is, of course, KE final minus KE initial. KE final, it ends at 0, so you don't have to worry about that. But that's just half mv squared. Half mv initial squared. Boom. Boom. And they're not going to sweat you with the negative over here and what that means. But look at the way. So you could get this work via FD, difficult here because they didn't give you F or D, or via delta KE. So this is really a nice problem. And same junk over here. This could be the kind of the last-ish one on this. Anyway, how much does the internal energy increase? So they want to know about delta Q. Right? That's the thing we're looking for. Well, we don't have like a, we can put MCAT. We can recognize that this is the same thing as WF, which is FF times D. Okay? FF times D. And look what they gave you. They gave you the weight of the block. Like, don't forget forces. Go back to it. Right? So you know FG. It's on a level steel surface. So the normal force is going to be the same as FG, Fn. It's sliding. Maybe it's sliding to the right. Who cares? So then the frictional force will be to the left. The displacement, though, is to the right. It's sliding this way and slowing down. And they want to know about delta Q. You're not going to get delta Q. You're not going to MCAT this. It's not going to work. It doesn't apply to this scenario. But you do recognize it's WF, so the force of friction times displacement. This is a nice problem right here. Force of friction, of course, is coefficient times the normal. And now we're ready. Now we're ready. Because it's copper on steel. You can look up that kinetic coefficient. It's sliding. The normal is the same as the weight. The distance they gave you. Boom, you got your answer. So, you know, this is nice stuff. This last one down here, look at this funky thing. A box is pushed from rest a distance of 6 meters. Here's a force. Here's friction. This is actually, the friction does 40 joules of work, the work done by friction. What's the final kinetic energy? Ooh, when you get these complicated scenarios, listen, you know, I'm not even gonna mess with colors right here. You don't even have to get fancy. Little G for gravity, N for normal. You don't even want to write the letter F. You can survive. What's going on here? The box is being pushed this way. You got some push, and you got some friction back this way, right? And let's see. Cool. So they want to know about final kinetic energy. They're asking for KE. Now, of course, you could do half mv squared. That's one option. And, you know, you could figure that out. It may be a little funky, but you'll get there. Or, this is really a change in kinetic energy. They're asking for the final, started with nothing. Push from rest. You could also do the W net, the work done by the net force. And, you know, this one's a little bit of a layered problem. But anyway, you have F net here. And if you remember, you can do this with just the forces, that's fine. Or, if you remember, in this x direction, W done by that force plus W done by the frictional force is going to be the W net. You remember this all coming together once upon a time? So you actually know W by the friction force they told you was 40. However, here you do have to pay attention. If the displacement is this way, it's a negative 40. That's a negative 40. Let me make that negative very clear. Change of color. That's a negative 40. The work done by the pull force, the F, is just going to be F times D. 20 times 6, that's going to be 120. 120 minus 40 is, plus negative 40 rather, is 80. That's the W net. And they ask for, what's the kinetic energy? W net is kinetic energy. You're done. Done. All right, last thing, look at these graphs. You can just look at your formulas. You know, PES, average FS. We talked about this, but you should go check these out yourself. That's going to be direct. Direct. Work done on a spring is the change in PES. This is like very straightforward. WG is delta PEG. KE is, delta KE is F net D, so it's directly related. W to accelerate is delta KE. And WF is delta Q. Now, very important here. The slope of this graph, this graph, this graph, and this graph. I might ask you this. These are literally the same thing. So if WG is delta PEG, then the slope would be WG over delta PEG. If you divide both sides by delta PEG, you are left with delta WG over delta PEG. What's going to be on the right-hand side of that equation? It's not nothing. It's 1. Since these are the same thing, you'll end up with a 1. This is a 1, and this is a 1. You should know those. Don't be surprised you see that on the assessment tomorrow. The ones where they are equal, WG is, here are the 4 of them. That's the 4 I'm going to bother you on. Then those would have a slope of 1 because they're the same thing. These would not. PES, here the slope is going to be X, and here the slope is going to be D, but those there. All right, so you'll finish up the homework, and that's it. I'll post a little review thing, hopefully help you guys think about the assessment for tomorrow.